Beneath the quiet fields near Geneva, CERN's machines are searching for patterns no human eye can see. A particle appears for less than a heartbeat, then vanishes, leaving only traces in the detectors. Scientists do not call it terrifying because it is dangerous. It feels terrifying because it touches one of the deepest questions in physics: is the known map of reality complete, or is something still hidden underneath it? In this video, the story moves slowly from the giant underground collider to the smallest signs left by matter itself. Before it begins, please like this video, subscribe to the channel, and stay with the journey into CERN's quiet search for what may come next. On the western edge of Geneva, where fields, roads, offices, and low industrial buildings share the same quiet ground, CERN appears at first as a place of ordinary surfaces. The sky above it is open and changeable. Clouds move over the Jura mountains, and the distant Alps hold a pale edge of snow when the air is clear. Traffic passes through border roads between Switzerland and France. Buses stop near gates, cyclists move along marked lanes. People cross between buildings with badges, notebooks, laptops, and cups of coffee. The scene does not resemble a place where matter is studied at its smallest known scales. It resembles a working district, careful and practical, with concrete, glass, metal, and grass. CERN is the European Organization for Nuclear Research, a laboratory built for shared particle physics. Particle physics is the study of the smallest known pieces of matter and the forces that shape their behavior. The word nuclear remains in the name because the laboratory is founded in the middle of the 20th century, when research into atomic nuclei gives the field much of its language. In the present, CERN reaches beyond the nucleus and studies particles that are smaller than atoms. It does this through machines, detectors, and international cooperation. The surface of the site holds the visible part of that work. It is the outer skin of a deeper scientific landscape. The buildings are not arranged as monuments. They are placed for use. Some are offices, where researchers write code, compare measurements, meet in small rooms, and prepare talks. Some are workshops, where metal parts, cables, electronics, vacuum chambers, and support structures are designed, assembled, repaired, or tested. Some are control rooms, where screens show beams, temperatures, currents, pressures, and alarms. Some are cafeterias, where people from many countries sit close together, speaking in several languages. The daily rhythm is steady. Experiments that may take years to prepare are supported by simple routines, repeated across mornings and afternoons. CERN's surface world is international in a practical sense. Scientists, engineers, technicians, students, administrators, and visiting teams arrive from universities and institutes across many countries. The work depends on people who build magnets, align sensors, handle cryogenic systems, maintain computers, design software, interpret statistics, and publish results. A single measurement can require years of planning and thousands of careful checks. The public may hear a short phrase about a new particle or an unusual asymmetry, but on the ground the achievement rests on slow coordination. No single corridor carries the whole meaning. The laboratory is a network of tasks joined by a shared aim. The calm surface also reflects a careful culture of control. CERN does not search for the unknown by letting nature run wild. It creates controlled conditions, measures them with disciplined instruments, and separates real signals from background patterns. The word discovery has a strict meaning in this setting. It is not a sudden impression. It is a result supported by data, checked against known processes, and tested for the chance that the pattern could arise from random fluctuation. In particle physics, certainty is approached through statistics, repeated analysis, independent review, and comparison with theory. A discovery changes understanding only within the limits of what evidence shows. The title of a discovery can sound large because the questions are large. Matter itself is at stake. The familiar world is made of atoms, and atoms are made of smaller pieces. The behavior of those pieces depends on forces that cannot be seen directly on the surface of a road or building. CERN's work is connected to questions about why matter has structure, why particles have mass, why some particles decay quickly, and why the visible universe contains matter in the form that it does. These questions are not solved by a single announcement. They are refined by measurements, until theory becomes more exact or begins to show a gap. Above ground, nothing in the landscape appears terrifying in a physical sense. The site is regulated, monitored, and built around safety procedures. The machines are designed to contain beams, manage radiation, control access, and protect workers and visitors. The unease sometimes attached to particle physics comes from scale and unfamiliarity, rather than from uncontrolled danger. Human senses are not made to picture particles that exist for tiny fractions of a second, or forces that act inside matter. The mind meets an invisible realm and fills it with drama. Scientific work moves in the opposite direction. It removes drama from the unknown by giving it measurements, names, limits, and error bars. CERN's surface also shows the patience required for modern physics. A path between buildings may be crossed by a doctoral student who studies one narrow decay pattern. Nearby, an engineer may be concerned with the thermal behavior of a detector component. A computing specialist may watch data transfer across storage systems. A technician may inspect a connector. Each task appears small from the outside. Together, they allow a laboratory to notice rare events hidden among vast numbers of ordinary ones. The outer region of the story is therefore not a place of spectacle. It is a place where order is built so that the hidden world can be approached without haste. Vineyards, farms, suburbs, and mountain views belong to a familiar European border region. Weather changes slowly across the day. Rain darkens the pavement. Sunlight catches windows. In winter, the air can be sharp and still. In summer, the grass grows around fences and service roads. The laboratory remains part of this ordinary setting. Delivery trucks arrive. Meetings begin. Visitors pass through exhibitions that explain particles with models and displays. School groups learn that the visible universe is not simple, even though it seems solid. The outer view remains calm because science here begins with patient observation of what is already present. CERN's meaning at the surface is therefore not found in a single dramatic object. It is found in the way many ordinary structures support an extraordinary inquiry. The laboratory stands as a public place of research, funded and used by nations that choose to study nature together. Its discoveries are not acts of fear, but careful additions to knowledge. The word terrifying belongs more to the feeling of standing before the unknown than to the work itself. At the outer edge of the topic, the setting is quiet, regulated, and human. The first layer is a landscape of buildings and people, where the smallest questions begin in the most ordinary light. Around CERN, the land does not belong to one simple boundary. It spreads across a region where Switzerland and France meet in a soft pattern of roads, villages, fields, fences, and customs crossings. Geneva lies to the east, close to the southern end of Lake Geneva, where the water reflects grey skies, low clouds, and bright mountain light. To the west and north, the land rises and opens toward the Jura. To the south and southeast, the Alps remain visible when the air is clear. The laboratory sits within this border landscape, not separate from it, but threaded through it. The geography is calm, practical, and layered. The Geneva region gives CERN a particular shape. The surface buildings are placed near the border, while the underground accelerator ring extends beneath both Swiss and French ground. This means the laboratory is not only international in its people and institutions, it is international in its physical placement. The ground itself is shared. A person walking along a road near the site may pass from one country to another with little drama, while far below, the same border becomes almost irrelevant to the circular path of the machine. The land above keeps its maps and signs. The machine below follows geometry, geology, and engineering. This outer regional layer matters because large particle accelerators require space, stability, and support. They're not placed only according to symbolism. They depend on underground conditions, access points, transport links, power systems, cooling facilities, safety zones, and connections to universities and cities. CERN grows in a place that can support a major scientific infrastructure while remaining close to a city with international institutions. Geneva already carries a tradition of diplomacy and cross-border work. CERN adds another kind of cooperation, less concerned with political negotiation and more concerned with measurements of matter. The land around CERN appears gentle, but beneath it the geology must be understood with care. Tunnels require stable rock and soil, shafts require safe access, caverns require support, water movement, ground pressure, and construction limits all matter. The accelerator complex is not an abstract circle drawn on a map. It is a built form placed into real Earth. Engineers and surveyors must translate the planned path into the uneven conditions below fields and towns. The outer region is therefore not just a backdrop. It is the container that allows the deeper instrument to exist. At the surface, the border region keeps its daily life. In French villages near the laboratory, houses stand with tiled roofs, small gardens, and local roads. In Swiss areas, trams, buses, and city streets connect the site to Geneva. Airports, train stations, and highways make it possible for visiting researchers to arrive from many parts of the world. A scientist may land in Geneva, take local transport, and reach a place where a meeting concerns a particle that lives for an extremely short time. The scale shifts quietly from global travel to regional streets to buried machines to subatomic events. The laboratory's position also shapes its culture. People move through a region where languages and systems overlap. French is common in the surrounding area, but English often serves as a shared language inside international collaborations. Administrative rules, safety procedures, transport routines, and housing arrangements all reflect the border setting. Many workers live on one side and work on the other. The daily pattern of research includes crossing lines that are visible on maps, but almost invisible in routine movement. This ordinary crossing gives the place a steady sense of shared purpose. The land above the accelerator ring includes farms and developed areas, and much of the machine remains unseen by those who pass over it. A road may run above a section of tunnel, a field may cover part of the ring. A village may sit near a technical site that connects downward through a shaft. The surface does not announce the full structure beneath it. This hidden placement gives the region a quiet contrast. Ordinary ground carries an instrument built to study conditions far removed from ordinary experience. The contrast is not supernatural. It is the result of engineering placed beneath familiar land. CERN's public identity often attaches to the Large Hadron Collider, but the regional landscape contains a wider accelerator complex. Smaller machines feed particles into larger ones, test areas, experimental halls, offices, and support systems are spread through the site. The geography is therefore not a single point. It is a distributed scientific terrain. Each part has a function, and each function connects to another. The outer map of roads and buildings mirrors an inner map of beams, transfers and measurement points. The region becomes a working organism, but one made from concrete, cables, magnets, software, and human planning. The presence of the laboratory has also shaped the area's relationship with science education and public understanding. Visitors come to exhibitions and guided areas. Schools and universities use CERN as an example of international research. Local communities live near a facility that is famous across the world but physically quiet in daily life. The laboratory does not dominate the skyline. It is not a tall tower or a large factory plume. It is mostly low, dispersed, and partly hidden. Its importance is measured not by height but by depth, precision, and collaboration. The Geneva border setting also helps place the emotional tone of the story. The phrase "new discovery" can suggest a sudden shock, but in this region, discoveries emerge from a long, shared system. They're carried by roads, offices, meeting rooms, workshops, and data centers as much as by the underground ring. They depend on a landscape that supports patience. The region holds the outer conditions for inner measurement. It supplies access, stability, and continuity. It allows many nations to gather in one working place and look inward at matter without turning the work into spectacle. As the view remains at the regional scale, CERN is seen not as a single mysterious object, but as a carefully embedded laboratory. It sits among mountains, borders, fields, roads, and towns. Its scientific reach is enormous, yet its surface presence stays modest. The surrounding land does not reveal the particles being studied, but it makes the study possible. The Geneva border is a threshold between ordinary geography and hidden structure. It is the second layer of the path inward, a calm region where maps, nations, and Earth meet the first outlines of a machine designed to measure the smallest known pieces of nature. Below the fields, roads, service buildings, and border crossings. The Large Hadron Collider forms a vast underground ring. It lies in a tunnel that follows a circular path beneath Swiss and French ground. The circle is not visible from above, and its presence is known through access points, maps, technical sites, and the careful language of engineers. At this layer of the story, the surface world gives way to a built underground structure. The ring becomes the main region. It is not a symbol or a hidden chamber of mystery. It is a long, precise machine placed inside the Earth to guide particles around a controlled path. The tunnel is about 27 kilometers in circumference. It is large by human standards, yet narrow compared with the landscape above it. A person standing inside it sees a curving corridor of concrete, equipment, pipes, cables, magnets, supports, signs, and lighting. The curve is gentle because the ring is so wide. The wall does not seem to bend sharply. Instead, the tunnel moves away in a steady arc, almost like a road that never reaches a visible end. The space is functional. Every object has a reason for being there. The tunnel is designed for operation, access, maintenance, and safety. The Large Hadron Collider is called a collider because it brings particles into head-on collisions. The word hadron means a particle made of quarks, held together by the strong interaction. Protons are hadrons, and they are the particles most often used in the collider's highest energy work. The underground ring is built to accelerate beams of protons to very high energies, guide them around the ring, and bring them together at selected points. The tunnel itself is the outer body of this machine. It holds the systems that make the beam path possible. The ring is not only an empty passage with a beam pipe, it contains thousands of magnets and many support systems. The magnets are essential because protons carry electric charge, and charged particles can be steered by magnetic fields. The ring bends the path of the beams so that they continue around the circle rather than moving in a straight line. Without the magnetic field, the protons would not remain in the circular path. The tunnel therefore becomes a place where invisible fields shape invisible beams. The concrete and metal are visible, but the most important action occurs through forces that cannot be seen directly. Many of the main magnets are superconducting magnets. Superconducting means that certain materials can carry electric current with no electrical resistance when cooled to extremely low temperatures. To reach this state, the magnets are cooled by liquid helium and complex cryogenic systems. Cryogenic means related to very low temperatures. The ring is therefore not only a machine of high energy, it is also a machine of deep cold. In one part of the imagination, particle collisions may seem hot and violent. In the actual tunnel, the ability to control such collisions depends on carefully maintained cold systems, stable currents, and exact engineering. The beam travels inside vacuum pipes. A vacuum is a space from which most matter has been removed. This is needed because protons must move around the ring without constantly striking gas molecules. Even a small amount of remaining gas can disturb the beam. The vacuum system creates a quiet inner path, emptier than ordinary air. Around it, magnets, instruments, and shielding form layers of control. The tunnel is a region of containment, not chaos. It narrows the possibilities for particles until they can be guided, accelerated, and measured with precision. The underground ring also depends on radiofrequency cavities. These are structures that use electric fields to give energy to the particles as they pass. The process is timed with great care. The protons do not move as a loose stream. They are arranged in bunches, and the accelerating fields are synchronized so that each bunch receives energy in the right way. The ring is therefore a clock as well as a circle. Its systems must keep rhythm across long distances. Timing errors, temperature shifts, alignment issues, and electrical instabilities are all matters of concern. The machine works because many forms of precision are held together at once. The tunnel is connected to the surface through shafts and service areas. These access points allow equipment to be lowered, workers to enter during maintenance periods, and systems to be supplied. The ring is divided into sectors, and each sector has technical roles. Some areas contain magnets arranged in long sequences. Others are near experimental caverns, where the beams will later meet. At this region of the path, however, the focus remains on the ring itself. The outer machine that carries the beams. It is a circular infrastructure built for repeated controlled motion. Safety shapes the underground environment. During operation, access to the tunnel is restricted. The beams carry large stored energy, and particle interactions can create radiation in certain areas. Systems monitor conditions and control entry. When the machine is shut down for maintenance, teams follow procedures before working underground. These routines are part of the machine's design. A large accelerator is not simply switched on like a lamp. It is prepared, checked, cooled, aligned, monitored, and protected. The tunnel is quiet because it is governed by rules. The Large Hadron Collider is often described by its energy, but its size also matters. The wide ring allows magnets to bend very energetic particles without forcing them into too sharp a curve. Higher energy beams require stronger bending or larger circles. The tunnel was originally built for an earlier machine and later reused for the Large Hadron Collider, showing how scientific infrastructure can carry history within its walls. The present machine stands inside a path shaped by earlier work. Using old space for newer precision, the underground ring is therefore both a current instrument and part of a longer engineering memory. At this layer, the idea of discovery remains distant from headlines. The ring does not itself declare what nature contains. It prepares the conditions in which evidence can appear. It gives protons energy, keeps them moving, and brings them towards selected meeting points. The discovery process begins with the ability to make a controlled event happen many times, under known conditions, inside a machine whose behavior is measured constantly. The underground ring is the region where that control becomes physical. It is a vast, curved instrument beneath ordinary land, built to turn motion, cold, vacuum, magnetism, and timing into a path toward the inner structure of matter. Inside the underground ring, the work of the Large Hadron Collider becomes a matter of beams in motion. The particles do not begin at full energy, and they do not appear suddenly inside the main tunnel. They pass through a chain of machines that prepare them in stages. By the time they enter the largest ring, they are already moving close to the speed of light. The ring then gives them more energy and holds them in a path that circles again and again. At this layer, the machine is no longer only a tunnel filled with equipment, it is a controlled path for moving matter. The particles most often used for the highest energy collisions are protons. A proton is one of the particles found in the nucleus of an atom, and it carries a positive electric charge. Protons are small, stable under ordinary conditions, and useful for exploring high-energy physics. They are taken from hydrogen, the simplest element. A hydrogen atom contains one proton and one electron. When the electron is removed, the remaining proton can be guided by electric and magnetic fields. This simple starting point leads into one of the most complex instruments ever built. The beam is not a solid line. It is made of many bunches of protons, with each bunch containing a very large number of particles. These bunches move through the vacuum pipe in carefully timed groups. They pass around the ring in opposite directions, each beam held in its own path. The protons are so small and the pipe is so long that the work depends on exact control. A beam that seems powerful in total is also delicate in its shape. It must be focused, steered, corrected, and watched. The motion is continuous, but it is never careless. Magnetic fields guide the beams. Dipole magnets bend the particles around the ring. A dipole magnet has two magnetic poles and creates a field that can curve the path of charged particles. Quadrupole magnets focus the beam, working somewhat like lenses for moving charged particles. Other magnets correct smaller distortions. The result is not a simple circle drawn once and left alone. It is a constantly maintained orbit. The beam position is measured, adjusted, and stabilized. Small deviations can grow if they are not corrected. The machine therefore acts with quiet attention, keeping the particles close to the intended path. The protons receive energy from radio frequency cavities as they pass through specific parts of the ring. An electric field changes in time, and the timing is arranged so that the particle bunches are pushed at the right moment. The process is similar in principle to a repeated, carefully timed nudge. Though the actual system is built with great precision, each pass can add energy, and many passes bring the beam to the planned level. The particles move so quickly that further energy does not make their speed increase much in ordinary terms. Instead, their energy rises in a relativistic way, connected to Einstein's description of motion near the speed of light. As the energy rises, the beams become more demanding. The magnetic fields must hold them with greater strength. The orbit must remain stable. The focusing must keep the bunches narrow enough for useful collisions. The vacuum must remain clean. The cryogenic systems must keep the superconducting magnets cold. Every support system becomes part of the beam's motion. A proton bunch circling the ring appears, in human imagination, as almost weightless and invisible. Yet the machine surrounding it is massive, cold, and precise. The contrast is central to the collider. Huge structures serve tiny particles. The beams move in opposite directions because collision experiments need particles to meet head-on. When two beams collide, the available energy can be concentrated in a small region. This does not mean that whole protons simply break like stones. Protons are made of quarks and gluons, and the collision involves their inner components. Gluons are particles associated with the strong interaction, the force that binds quarks together. In high-energy collisions, the energy can produce many particles, some familiar and some rare. The beam motion creates the conditions, but the details of each event are governed by quantum physics, where outcomes are described by probabilities. The beam must also be protected from itself. A high-energy beam stores enough energy to damage equipment if it is lost in the wrong place. For this reason, the collider includes beam monitoring, collimators, and beam dump systems. A collimator is a device that removes particles that stray too far from the beam path. A beam dump safely absorbs the beam when it must be removed from the machine. These systems show again that the work is controlled. The beam is not allowed simply to wander until it stops. It is shaped, cleaned, and, when necessary, sent away in a planned manner. During operation, people in control rooms follow the state of the beams through screens and alarms. They do not see the protons directly. They see measurements of intensity, position, losses, currents, temperatures, and other signals. The beam exists for them as a living set of numbers, traces, and conditions. When something changes, the machine protection systems respond. Human operators and automated systems work together. The calm surface of a screen may represent a beam moving through many kilometers of underground pipe. The hidden motion is translated into information that can be understood and acted upon. The phrase new discovery remains far from this region because a beam alone is not a discovery. It is preparation. It is the controlled delivery of energy and matter to selected points. Without stable beams, detectors cannot collect useful data. Without careful timing, collisions cannot be placed where instruments are ready. Without clean vacuum and strong magnets, the particles cannot complete their path. The beam is the moving thread that connects the whole machine. It is also the boundary between engineering and measurement, because it carries ordinary protons toward conditions where rare processes may become visible. In this inner layer of the accelerator, fear gives way to repetition. Protons circle the ring many times. Systems hold their rhythm. The beams are adjusted, accelerated, squeezed, separated, and brought toward collision according to planned procedures. The motion is fast beyond ordinary senses, but the work around it is slow, structured, and exact. The machine does not ask nature to reveal everything at once. It creates countless controlled moments, each one small, each one measured. The beams in motion are the quiet current of the collider, carrying matter through a cold and empty path beneath the borderland. At selected places around the underground ring, the two beams are brought together. These places are called collision points, and they are the thresholds where the controlled motion of the accelerator becomes the raw material of observation. The protons travel in opposite directions through separate paths until the machine guides them into the same narrow region. There, bunches pass through one another at extremely high energy. Most protons do not strike in the simple way imagined for solid objects. They are tiny compared with the space in which they move, and their inner parts interact according to probabilities. Yet when interactions do occur, they create sprays of particles that carry information outward. The collision points are not empty intersections. They sit at the hearts of major experiments. Around them stand huge detectors, each designed to record the results of particle interactions. ATLAS and CMS are general-purpose experiments, built to study a wide range of high-energy processes. ALICE studies collisions involving heavy ions, where matter can reach conditions similar to those that existed very early in the universe. LHCb studies particles containing beauty quarks. With special attention to differences between matter and antimatter, each experiment surrounds a collision region with instruments arranged to catch signs of what happens in a space far smaller than an atom. A collision point is a small physical region held within a much larger structure. The beams are squeezed before they meet so that the proton bunches become narrow and dense. This increases the chance that protons will interact. The focusing must be exact, because the useful collision zone is tiny. Magnets near the experiments shape the beams and guide them into place. These magnets must work with the detector environment, the tunnel geometry, and the demands of safety. At this layer, the inward path reaches a meeting place, where motion becomes interaction and interaction becomes data. When two protons collide at high energy, the event is not a collision of featureless balls. Each proton contains quarks and gluons. Quarks are fundamental particles that combine to form hadrons, and gluons are connected with the strong interaction that binds quarks inside a proton. These components are always active in a quantum sense. At high energy, a collision often involves one component from each proton, while the rest of the proton material becomes part of the surrounding event. The result may include many particles moving outward in different directions. Some are common, some are rare, some decay almost immediately into other particles. The experiments must separate rare events from ordinary ones. The collider produces enormous numbers of collisions, and only a small fraction can be stored in full. This creates the need for trigger systems. A trigger is a fast decision system that selects events likely to be useful for analysis. It works in stages, using rapid information from the detector to decide whether an event should be kept. The trigger does not know the final meaning of the event. It only applies carefully designed criteria. This first selection is one of the earlier steps in turning a collision into scientific evidence. At the collision point, energy becomes a form of possibility. According to modern physics, energy can appear as mass when conditions allow, and new particles can be produced if enough energy is concentrated in the interaction. This does not mean anything can appear without rules. Conservation laws still apply. Electric charge, energy, momentum, and other quantities must balance. Quantum fields determine which processes are allowed and how often they occur. The collision point is therefore not a place of unlimited creation. It is a place where the rules of nature are tested under controlled, high-energy conditions. The major experiments differ in shape because they are built around different scientific purposes. ATLAS is very large, with layers arranged around the collision point to measure many kinds of particles. CMS is more compact but extremely dense, using a strong magnetic field and precise instruments. ALICE is designed to study dense matter created when heavy ions collide. LHCb has a forward design, because the particles it studies are often produced close to the direction of the beam. These designs show that observation is not neutral in a simple way. The detector is shaped by the questions it is meant to ask. Even so, Each collision point shares the same basic challenge. The important event occurs in a space that no eye can see. The particles created may live too briefly to reach the detector directly. The detector records what remains after decays, bends, deposits, and interactions with material. A particle with electric charge may leave a track. A particle carrying energy may create a shower in a calorimeter, which is a device that measures energy by absorbing particles. A MON may pass through outer layers and leave signs in dedicated chambers. The original collision must be reconstructed from these outward traces. The collisions are also surrounded by background. Some signals come from the event of interest. Others come from additional proton interactions in the same bunch crossing, from detector noise, from stray particles, or from known processes that resemble the pattern being studied. Scientists do not treat a striking pattern as proof by itself. They compare data with simulations, control samples, and known physics. They estimate background and uncertainty. A result becomes meaningful only after the ordinary sources of similar signals are understood. At the collision point, the first act is brief, but the interpretation is long. This region gives the word discovery its first physical footing. A new particle or rare process cannot be announced merely because a collision looks unusual. The evidence must appear as a consistent excess, a pattern, a decay path, a mass peak, or another measurable feature that remains after careful checks. Many collisions are needed. Many events are rejected. Many possible errors are studied. The collision point provides the events, but the claim grows only later through analysis. The controlled meeting of beams is the doorway, not the conclusion. The atmosphere around these points during operation is not theatrical. The beams meet inside shielded experimental caverns. The detectors record signals electronically. People watch displays in control rooms, check rates, monitor detector health, and manage data quality. The collisions themselves happen far too quickly and too deeply inside the instruments for human senses. What reaches the surface is information, arranged in streams and files. The violence of the microscopic interaction is contained inside a calm system of measurement. The scale difference is immense, yet the purpose remains simple: bring particles together, observe what emerges, and compare the results with the laws already known. At this fifth layer, the path has moved from landscape to ring, from ring to beam, and from beam to meeting point. The collision point is the place where the collider becomes an experiment in the strongest sense. It is where prepared protons stop being only moving particles and become probes of inner structure. Each event is small and short, but the collection of events is large and patient. The discovery that may sound frightening in a title begins here as a quiet, repeated act inside a detector where beams cross, particles emerge, and nature leaves patterns that must be read with care. Around each collision point, detector layers form a kind of scientific shell. The collision itself happens near the center, in a region too small and too brief for direct sight. From that center, particles move outward. Some travel only a tiny distance before they decay. Some pass through inner sensors and leave narrow tracks. Some deposit their energy in dense material. Some continue into outer chambers. The detector does not see the original event as an image. It records many separate traces, each one connected to charge, energy, direction, timing, or penetration. From these traces, the event is rebuilt. The innermost detector layers sit closest to the beam pipe. They are designed to measure the paths of charged particles with great precision. A charged particle is a particle with electric charge, either positive or negative. When it passes through sensitive material, it can leave tiny signals. These signals mark points along its path. A computer later connects the points into a track. The track shows where the particle moved after the collision. It can also show whether the particle came from the main collision point or from a secondary point slightly away from it. This difference is important because some unstable particles travel a short distance before decaying. The inner tracking systems are built from fine layers of silicon sensors and other precision devices. Silicon is useful because charged particles crossing it can create small electrical signals. These signals are collected and turned into data. These sensors must be placed with extraordinary care. Their positions must be known accurately, because a small error in alignment can affect the reconstructed path. The detector is therefore not only a receiver, it is a measured object itself, its shape. Position, temperature, and response must be understood before its signals can be trusted. A magnetic field surrounds much of the tracking region. Charged particles bend as they move through a magnetic field. The amount of bending depends on the particle's momentum, which is a measure of motion linked to mass and speed. A particle with higher momentum bends less. A particle with lower momentum bends more. The direction of bending also shows whether the charge is positive or negative. By measuring curved tracks, scientists estimate momentum and charge. The detector turns invisible motion into geometry. The curve of a track becomes part of the language of evidence. Farther outward, calorimeters measure energy. A calorimeter is a detector layer that absorbs particles and measures the energy they release. Electromagnetic calorimeters are designed mainly for electrons and photons. Hadrons, such as protons, neutrons, and particles made of quarks, are measured in hadronic calorimeters. When a particle enters a calorimeter, it can produce a shower of secondary particles. The shower spreads through the material, and sensors measure the deposited energy. The original particle may no longer exist as it entered, but its energy leaves a pattern. This pattern helps identify what kind of particle passed through and how much energy it carried. Beyond the calorimeters, some detectors include muon systems. A muon is a heavier relative of the electron. It carries electric charge and can pass through large amounts of material. Because many other particles are stopped earlier, a signal in the outer muon chambers can be a strong sign that a muon has crossed the detector. Muon measurements are important in many analyses, including studies of rare decays and heavy particles. The outer layers therefore act like a final screen, catching particles that survive the inner material. Not every particle leaves a direct signal. Neutrinos, for example, interact very weakly and usually pass through detectors without being measured. Their presence is inferred from missing momentum in an event, if the measured particles do not balance as expected. The missing part may indicate particles that escape detection. This inference must be handled carefully, because detector limits and measurement uncertainties can also create apparent imbalance. The absence of a signal can carry information, but only when the rest of the event is understood. The detector layers must work together. A track in the inner detector may match an energy deposit in a calorimeter. A track may continue outward to a muon chamber. An energy deposit without a matching charged track may suggest a photon or a neutral particle. The combination of signals gives particle identification, meaning the process of deciding which particle type most likely produced the observed pattern. Identification is never a matter of a single clue alone. It depends on many measurements, compared with known detector behavior and simulated events. Timing is also part of the detector's task. Collisions occur in rapid sequence, and signals must be assigned to the correct bunch crossing. A bunch crossing is the moment when two proton bunches pass through each other at a collision point. In busy running conditions, several proton-proton interactions can happen during the same crossing. This is called pile-up. Pile-up means that tracks and energy deposits from multiple interactions overlap in the detector. Scientists must separate the event of interest from additional interactions that occurred at nearly the same time. The detector layers provide enough spatial and timing information to help untangle this crowded picture. The data flow from these layers is enormous. The detector electronics must read signals, digitize them, apply early selection, and send information to computing systems. Most collisions are not stored in full detail. The trigger system selects events that meet scientific criteria. This means the detector is not only a passive recorder, it is part of a chain that decides which moments will be kept for later study. These decisions are based on known physics goals, detector capabilities, and the limits of storage and processing. The first record of a possible discovery is therefore shaped by both nature and instrument design. Calibration gives the detector its reliability. Calibration means adjusting and checking the detector response using known signals. If a known particle has a known mass or behavior, it can help test whether the detector is measuring correctly. Alignment, energy scale, timing, efficiency, and noise are all studied. Scientists compare real data with simulations and with control samples. A control sample is a set of events used to check a method because its properties are already well understood. Without calibration, an unusual pattern might be mistaken for new physics when it is only an instrumental effect. The detector must know itself before it can reveal nature. At this layer, the path inward reaches the instruments that translate collisions into evidence. The detector surrounds the event like a carefully built memory. It does not preserve the collision directly. It preserves consequences, tracks, curves, showers, timings, and missing balances. Every layer filters the event through matter, electronics, and analysis. The result is not less real because it is indirect. It is the ordinary way particle physics works. The inner world is known through traces left in outer material. CERN's discoveries begin as these traces, quiet signals arranged in layers, waiting to be compared with the patterns already expected from the known laws of matter. Among the major experiments at the Large Hadron Collider, LHCb occupies a special region of purpose and design. Its name comes from Large Hadron Collider beauty, because much of its work focuses on particles containing beauty quarks. A beauty quark is a heavy quark, also called a bottom quark, and it appears inside unstable particles that decay in ways useful for studying the deep rules of matter. LHCb does not surround the collision point in the same broad shape as some other detectors. It is built with a forward geometry, extending mainly along one side of the beam direction, because many of the particles it studies are produced close to that direction, after proton collisions. This design gives LHCb a distinct place in the inward path. It is not the largest detector at CERN, but it is highly specialized. Its instruments are arranged to track particles, identify them, measure their momentum, and reconstruct decay chains with exceptional precision. A decay chain is the sequence of transformations that occurs when an unstable particle changes into lighter particles. Since many particles containing beauty or charm quarks live only briefly, their presence must be inferred from the particles they leave behind. LHCb is built to notice those signs in great detail. The experiment sits around one of the collision points of the Large Hadron Collider. There, protons meet at high energy and produce many particles, including some that contain heavy quarks. Heavy quarks are important because their mass and decay behavior make them sensitive to subtle effects in the Standard Model. The current theory that describes known fundamental particles and several of their forces, the standard model is very successful, but it does not explain every known feature of the universe. LHCb measures heavy flavor particles, meaning particles that contain heavy quarks such as charm and beauty, to test the theory with care. The first layer of LHCb's work is tracking. Close to the collision region, precise detectors record charged particles as they move away from the interaction point. Some heavy flavor particles travel a small distance before they decay. This distance may be tiny by ordinary standards, but the detector can measure it. The place where such a particle decays is called a secondary vertex. A vertex is a point where particle tracks begin or meet. By finding secondary vertices, LHCb can identify events where short-lived heavy particles were present. This ability is central to its science. Farther along the detector, magnetic fields bend charged particles. The curvature of each track allows researchers to estimate momentum and charge. Momentum matters because it helps reconstruct the mass of a parent particle. When several decay products are measured, their energies and momenta can be combined to infer what unstable particle produced them. A narrow peak in a reconstructed mass distribution can indicate a known particle or support evidence for a newly observed one. The result depends on precision, background estimates, and repeated checks, not on a single event. Particle identification is another key part of LHCb. Many decay products can look similar if only their tracks are measured. Pions, kaons, protons, electrons, and muons must be separated as reliably as possible. LHCb uses systems that respond differently to different particle types. Ring imaging Cherenkov detectors help distinguish particles by the light they emit when passing through material faster than light travels in that material. This does not violate the speed limit of light in vacuum. It is a property of light moving more slowly through matter. The resulting light pattern helps identify the particle. Calorimeters and muon chambers add more information. Calorimeters measure energy from particles that deposit it in dense material. Muon chambers identify muons that pass through other layers. These systems allow LHCb to reconstruct decays involving different final particles. Some rare processes include muons, making their accurate identification especially important. Each layer improves the experiment's ability to separate true signals from background. The detector's strength lies in combining many partial signs into one coherent picture. LHCb's focus on matter and antimatter differences gives it a quiet but profound role. Antimatter particles have the same mass as their matter partners, but opposite electric charge and other opposite properties. When matter and antimatter meet, they can annihilate into other forms of energy and particles. In the known universe, matter is far more common than antimatter. The standard model contains some matter-antimatter asymmetry, called CP violation. CP violation means that the behavior of particles changes slightly when matter is replaced by antimatter and spatial directions are reversed. The amount known in the standard model is not enough by itself to explain the observed dominance of matter in the universe. Measurements at LHCb help test this imbalance in controlled particle decays. The experiment also studies charm quarks. A charm quark is another heavy quark, lighter than the beauty quark but heavier than the up, down, and strange quarks that form much ordinary matter. Charm particles decay quickly, and their patterns can reveal how the strong and weak interactions work together. The weak interaction is the force responsible for many particle decays. By comparing large numbers of charm and beauty decays, LHCb can search for tiny differences from expected behavior. These differences, if confirmed, may point toward incomplete parts of current theory, but each possible sign must survive careful statistical and experimental tests. The word terrifying does not fit the actual atmosphere of LHCb's work. The detector is not built to unleash danger, it is built to measure rare and delicate patterns. What may feel unsettling is the possibility that familiar matter rests on rules still not fully known. LHCb looks into that uncertainty by studying particles that appear briefly and vanish into decay products. The uncertainty is intellectual, not uncontrolled. It is the quiet pressure of a question that remains open after decades of precise theory. The experiment's discoveries often concern particles with unfamiliar names, narrow lifetimes, and complex internal structures. Such results may sound remote from daily life, yet they refine knowledge of the forces that shape matter. A newly observed particle does not necessarily overturn physics. Often, it confirms that the strong interaction can arrange quarks in a predicted way. Sometimes, a measurement places tighter limits on possible unknown forces. Sometimes, an anomaly becomes less significant as more data arrive. LHCb lives within this careful range, where discovery and caution remain close together. At this layer, the path has narrowed from the shared collision points to one specialized experiment. LHCb stands as a forward-looking instrument in both physical and scientific senses. It watches particles that move along the beam direction. It also watches for small departures from expected patterns. Its region is one of precision rather than size, patience rather than spectacle. The heavy particles it studies are born in proton collisions and fade almost immediately, but their traces remain long enough for the detector to gather them. In that brief passage, LHCb finds one of CERN's most sensitive ways of asking how matter behaves when examined close to its hidden rules. Within the region of LHCb's measurements, the focus moves inward to heavy quark matter. Quarks are fundamental particles, meaning that current evidence does not show them to be made of smaller parts. They come in several types, called flavors. The lightest quarks, up and down, form protons and neutrons, which make up atomic nuclei in ordinary matter. Other quarks are heavier and less stable in common conditions. Charm and beauty quarks belong to this heavier family. They are not found freely in everyday material, but they can appear in high-energy collisions and become bound inside short-lived particles before those particles decay. Heavy quarks matter because they bring mass, instability, and structure into the experiment. A charm quark is heavier than up, down, and strange quarks. A beauty quark is heavier still. Their larger masses make them useful probes of the Standard Model. They can decay through the weak interaction, and their decay paths can be measured in detail. At the same time, they are held inside particles by the strong interaction, the force that binds quarks together. Their behavior therefore connects two major parts of particle physics: the force that builds composite particles and the force that allows many of them to transform. A quark is never observed alone in ordinary experiments. This is because of confinement, a property of the strong interaction. Confinement means that quarks remain bound inside larger particles rather than appearing as isolated objects. When high-energy collisions produce quarks, the strong field around them leads to the creation of hadrons. Hadrons are particles made of quarks, and they include baryons and mesons. A baryon contains 3 quarks. A meson contains a quark and an antiquark. An antiquark is the antimatter partner of a quark. Heavy quarks become part of these short-lived hadrons, where their presence can later be inferred from decay products. In LHCb, charm and beauty hadrons are created in proton-proton collisions. They move away from the collision region and then decay after traveling a small distance. This small displacement is one of the main ways the detector recognizes them. The particle itself may not leave a full track from beginning to end, but its decay products do. When several tracks appear to begin from a point slightly separated from the main collision point, the event may contain a heavy flavor decay. The geometry of that separation becomes a clue. The detector reads distance on a scale far smaller than the width of a human hair, and from that distance it reconstructs a particle that no longer exists. Charm quarks often appear inside particles such as D mesons or charmed baryons. Beauty quarks appear inside B mesons and beauty baryons. These names are simple labels for complex internal systems. In each case, the heavy quark is bound with lighter quarks or antiquarks. The exact arrangement determines the particle's charge, mass, lifetime, and decay possibilities. Some combinations are common enough to be studied in large numbers. Others are rare and require enormous data sets. The presence of a heavy quark gives the particle a distinct place in the family of matter. The strong interaction inside these particles is not easy to calculate in every detail. At short distances and high energy, the theory of the strong interaction, called quantum chromodynamics, can be treated with certain mathematical methods. Quantum chromodynamics describes quarks and gluons. At the lower energies inside bound hadrons, the force becomes strong in a way that makes simple calculations difficult. Scientists use lattice methods, models, and experimental measurements to understand the possible structures. Heavy quark particles are especially valuable because they provide tests of how quarks bind when one or more of them has large mass. The inner life of a heavy hadron is active, but not in a way that resembles small balls orbiting one another. Quarks are quantum objects. Their positions and motions are described by probability patterns, and the gluon field between them carries the strong force. A particle with charm or beauty is a bound state of fields and energy, not a miniature mechanical system. Still, plain language can say that quarks are held together, share momentum, and form a measurable particle with a definite mass and charge. This particle then follows the rules of decay until it changes into lighter particles. Heavy quark matter also helps reveal the weak interaction. When a charm or beauty quark decays, it changes into another kind of quark through the weak force. This process may produce other particles, including leptons such as electrons or muons, and neutrinos that often pass through detectors without direct measurement. The pattern and rate of these decays are predicted by the Standard Model. LHCb compares those predictions with data. A small difference can be important, but only if it remains after uncertainties, backgrounds, detector effects, and statistical fluctuations are carefully studied. Some studies focus on rare decays. A rare decay is a transformation that happens very infrequently compared with more common paths. Rare decays are useful because unknown physics, if it exists at higher energy scales, may slightly change their rates or angular patterns. Angular patterns describe the directions in which decay products emerge. Since rare decays have small event numbers and significant backgrounds, they demand careful analysis. In heavy quark matter, rarity is not a weakness. It is one of the ways hidden effects may become measurable, if they are present. Other studies focus on spectroscopy. Spectroscopy in particle physics means measuring the masses and properties of particles to understand their internal structure. This is similar in spirit to how light spectra reveal atoms, but here the spectrum is a family of hadrons. New hadrons containing charm or beauty quarks add points to this family. Their masses, widths, lifetimes, and decay modes show how quarks can combine. Many such discoveries do not break the Standard Model. They deepen the map of the strong interaction, especially in regions where calculations are difficult. The phrase new discovery may refer to a newly observed hadron, a rare decay, or a measurement that differs from expectation. Each kind of result has a different meaning. A new hadron shows that quarks can bind in a particular arrangement. A rare decay measurement tests the weak interaction and possible contributions from unknown particles. A matter-antimatter difference tests symmetry. Heavy quark matter is the shared inner region where these results originate. It is not a single object, but a family of brief, structured states produced in collisions and read through their remains. At this depth, the story becomes quieter and more exact. Charm and beauty quarks are heavy, unstable, and hidden inside particles that vanish almost as soon as they form. They cannot be held in a container or placed under a microscope. They are known through decay lengths, track patterns, reconstructed masses, and rates. Their importance comes from the way they connect the stable matter of the everyday world to unstable forms that reveal deeper rules. Heavy quark matter is a narrow, fleeting region of nature, but inside it CERN finds some of its most careful clues about how the known forces shape the particles that briefly exist and then pass into other forms. Inside the family of heavy quark particles, a new baryon draws attention because it contains two charm quarks bound with a lighter quark. A baryon is a particle made of three quarks. Protons and neutrons are the familiar baryons of ordinary matter, built mainly from up and down quarks. A doubly charmed baryon is more unusual. It contains two charm quarks, and this makes it a useful structure for studying how heavy quarks behave when they're held together by the strong interaction. The particle is short-lived, but its brief existence adds a clear point to the map of matter. The doubly charmed baryon observed by LHCb is known as the CCC++. Its name reflects its quark content and charge. It contains two charm quarks and one up quark. The two charm quarks are heavy compared with the up quark, so the particle is not balanced like a proton or neutron. Its internal structure gives physicists a system that is sometimes described as having two heavy quarks forming a compact pair, with the lighter quark moving in the strong field around them. This description is a simplified image, but it helps explain why the particle is scientifically valuable. It is a different arrangement of matter from the more familiar baryons. The discovery does not mean that a dangerous new substance has appeared. The baryon is unstable and decays very quickly. It exists only under high-energy conditions, and only for a tiny fraction of a second before transforming into other particles. Its importance comes from what it teaches about the strong force. The strong force holds quarks inside hadrons, but its behavior in bound states is difficult to calculate exactly. A particle with two charm quarks offers a special testing ground. Its mass, lifetime, and decay modes can be compared with theoretical predictions and with other known hadrons. To observe such a baryon, LHCb does not catch it directly as a lasting object. Instead, it reconstructs it from the particles produced when it decays. The detector records tracks from charged particles. It measures their momentum, identifies their types, and determines whether they appear to come from a common decay point. If the measured decay products fit a specific pattern, their combined mass can be calculated. When many events show the same combination clustering at a particular mass, a signal appears. This signal is not a photograph of the baryon. It is a statistical and geometric trace left by many brief decays. The GCC++ is observed through decay channels that include other particles containing charm. A decay channel is a particular set of particles produced when an unstable particle transforms. Different channels can be used to confirm the same parent particle. The more consistent the evidence across channels, the stronger the result becomes. LHCb's ability to identify charm particles and measure displaced vertices is central to this work. The doubly charmed baryon decays through a sequence of short-lived states, and each step must be reconstructed with care. The particle's mass is one of its most important measured properties. Mass in particle physics is not only a measure of how much matter seems present, it reflects the energy of the bound system, including the quarks and the strong field between them. Since quarks inside a baryon are not simply added like stones in a bag, the final mass depends on binding energy and quantum effects. Measuring the mass of a doubly charmed baryon helps test calculations of quantum chromodynamics in a region where heavy quark dynamics matter. Agreement with predictions strengthens confidence in the theory's methods. Difference would require careful study before any deeper meaning could be claimed. The lifetime of the particle is also important. A lifetime in particle physics often means the average time before an unstable particle decays. The CCC++ lives for an extremely short time, but LHCb can infer this because the particle travels a small distance before decay. The measured displacement, together with the particle's momentum, gives information about how long it lived. Lifetime depends on the weak interaction and the internal structure of the particle. For doubly charmed baryons, lifetime measurements help distinguish between theoretical models of how the two heavy quarks and the lighter quark influence decay. The existence of a doubly charmed baryon has been expected within the Standard Model. Its observation is therefore not a sign that the Standard Model has collapsed. Instead, it confirms that the strong interaction permits this kind of three-quark structure and provides new data where theory is difficult. This is a common form of progress in particle physics. A discovery can be important without being a revolution. It can fill a missing place in a predicted family. It can give sharper tests of calculations. It can turn an expected possibility into a measured fact. The word terrifying becomes misleading at this scale. Nothing about the baryon suggests a threat to Earth, matter, or the laboratory. The unsettling part, if there is one, is the reminder that ordinary matter is only one stable corner of a much larger particle landscape. Protons and neutrons are familiar because they last under everyday conditions. Heavy baryons are unfamiliar because they vanish almost immediately. Yet the same basic rules of quarks and forces connect them. The new baryon shows that matter has many possible arrangements, most of them hidden from daily experience because they are unstable. The discovery also shows the power of large data sets. A rare particle may be produced only in a small fraction of collisions, and its useful decay pattern may be rarer still. LHCb must gather many events, apply selection criteria, estimate backgrounds, and measure significance. Background means other processes that can imitate the signal. A real discovery requires showing that the observed pattern is unlikely to be only background fluctuation. In this sense, the baryon emerges not from one spectacular event, but from the weight of many consistent traces. The particle is brief, while the evidence for it is cumulative. Once observed, the baryon becomes part of a broader program of measurement. Researchers can look for related states, compare decay modes, refine its mass and lifetime, and test how well theoretical tools describe it. Other doubly heavy baryons may contain different combinations of charm, beauty, up, down, or strange quarks. Each one would add a different point to the map. The CCC++ is therefore an inward marker in the particle family, showing where heavy quark binding can be measured directly enough to guide theory. At this ninth layer, the path reaches a newly observed structure inside the already hidden world of heavy quark matter. The particle is not large, lasting, or visible, but it is real in the scientific sense because its traces repeat, fit a consistent decay pattern and survive careful analysis. It changes everything only in the modest and precise way science often changes everything, by making the map more complete, by reducing uncertainty, and by giving theory a sharper object to explain. The doubly charmed baryon is a quiet discovery, brief in nature and lasting in knowledge, held for a moment by the strong force before it decays into signs that a detector can read. Within the structure of particles such as the doubly charmed baryon, the inward path reaches the binding forces that hold quarks together. The strong interaction is the force responsible for this binding. It is one of the fundamental interactions of nature, alongside gravity, electromagnetism, and the weak interaction. In the context of hadrons, the strong interaction acts between quarks and is carried by particles called gluons. Gluons transmit the force that keeps quarks confined inside composite particles. This force does not weaken with distance in the same simple way as gravity or electromagnetism. Instead, it behaves in a manner that leads to confinement. Confinement means that quarks are not found alone under ordinary conditions. When an attempt is made to separate quarks, the energy in the strong field between them increases. If enough energy is supplied, it does not free an isolated quark. Instead, it can create a new quark-antiquark pair, leading to the formation of new hadrons. This process ensures that quarks remain bound within particles. In a baryon, 3 quarks are held together in a shared field of gluons. In a meson, a quark and an antiquark are bound together. The strong interaction is therefore not only a force that pulls particles together, it defines how they can exist. Inside a doubly charmed baryon, the presence of 2 heavy quarks changes the balance of the system. The charm quarks carry large mass, and their interaction with each other through gluons can create a compact core. The lighter quark moves within the combined field of this heavy pair. This picture is a simplified description, because in quantum chromodynamics the quarks are not fixed points. They are described by probability distributions, and the gluon field is dynamic. Still, the idea of a heavy pair with a lighter companion helps guide intuition about how the binding may differ from that in lighter baryons. The strength of the interaction depends on the energy scale. At very high energies and short distances, quarks behave almost as if they are free. This property is called asymptotic freedom. It allows certain calculations to be performed using methods that treat interactions as small corrections. At lower energies and larger distances inside hadrons, the interaction becomes strong and cannot be treated in the same simple way. This is why many properties of bound states are difficult to calculate exactly. Experiments provide essential guidance by measuring masses, lifetimes, and decay patterns. The mass of a hadron is not simply the sum of the masses of its quarks. A large part of the mass arises from the energy of the gluon field and the motion of the quarks within it. Energy and mass are related through relativistic physics. The bound system carries energy in its fields, and that energy contributes to its mass. This means that studying the mass of a particle such as the GCC++ is also a way of studying the energy of the strong interaction in that system. The measured value reflects both quark masses and binding dynamics. The strong interaction also determines how quarks arrange themselves in terms of color charge. Color charge is a property in quantum chromodynamics that is not related to visual color. It comes in 3 types, often labeled as red, green, and blue by convention. A stable hadron must be color neutral, meaning that its combination of color charges results in a balanced state. In a baryon, the 3 quarks carry different color charges that combine into neutrality. Gluons themselves carry color charge and can interact with each other, making the strong interaction more complex than electromagnetism, where photons do not carry electric charge. In systems with heavy quarks, certain approximations can sometimes be used. The large mass of the charm quark means that its motion can be slower in some respects compared with lighter quarks, and this can simplify aspects of the description. However, the full behavior still requires detailed study. Measurements of doubly heavy baryons help test these approximations. If theory predicts certain mass differences or decay rates, experiments can confirm or refine those predictions. Agreement strengthens confidence in the methods. Disagreement prompts further investigation into the assumptions and calculations. The decay of a doubly charmed baryon involves the weak interaction acting on one of its quarks. The strong interaction holds the particle together until decay occurs, but it also shapes the possible decay paths. The internal arrangement of quarks affects how likely certain decays are and how the final particles are distributed. The strong and weak interactions are therefore linked in the behavior of these particles. One force maintains the bound state, the other allows transformation. Observing both aspects together provides a more complete picture of particle dynamics. The study of binding forces extends beyond a single particle. By comparing different hadrons, scientists can look for patterns. Particles with one heavy quark can be compared with those with two. Particles with different combinations of light quarks can be compared. These comparisons reveal how the strong interaction responds to changes in mass and configuration. The results contribute to a broader understanding of quantum chromodynamics, especially in regions where direct calculation is difficult. Each measured particle becomes a data point in this effort. The concept of force at this level does not resemble the push or pull of everyday experience. It is expressed through fields, probabilities, and interactions that occur at extremely small scales. The language of quarks and gluons is abstract, but it is grounded in measurable effects, tracks in detectors, energy deposits, and decay patterns all carry the imprint of the strong interaction. The binding force is not seen directly, but it shapes every observed feature of a hadron. It determines whether a particle exists, how it behaves, and how it changes. In this region, the idea of a new discovery becomes closely tied to refinement. A newly observed baryon tests the binding force in a specific configuration. It does not overturn the concept of the strong interaction, but it sharpens its description. The discovery is part of a gradual process in which theory and experiment move together. The strong interaction remains one of the most challenging parts of the standard model to calculate in detail, and each new measurement helps reduce uncertainty in that challenge. The inward path has now reached the forces that give structure to the particles themselves. From landscape to machine, from beam to collision, from detector to particle, the focus has narrowed to the interaction that holds quarks in place. The strong force is not visible in the ordinary sense, but it is present in every hadron. In the doubly charmed baryon, it binds two heavy quarks and a lighter companion into a brief but measurable system. That system exists long enough to leave traces, and those traces carry information about one of the fundamental forces that shape the matter of the universe. Inside the life of an unstable particle, the next inward region is not a place but a change. A decay is the transformation of one particle into other particles. In everyday language, decay may suggest slow damage or fading. In particle physics, it means a rule-governed change from one state to another. The original particle does not crumble like stone. It transforms through fundamental interactions, and the products of that transformation carry away energy, momentum, charge, and other conserved quantities. For particles containing charm or beauty quarks, Decay is often the only way their existence becomes known. A particle such as a doubly charmed baryon lives for an extremely short time. It travels a small distance from the collision point and then changes into other particles. The detector does not hold the original baryon. It records the charge tracks and energy deposits of the particles that appear after the decay. These products may themselves include unstable particles, which decay again. The result is a chain. A parent particle creates daughters, and some daughters become parents to further products. The observed event is a family of traces spreading outward from one or more points. The first clue in many heavy flavor decays is displacement. The main proton collision creates many particles at a primary vertex. A heavy particle may move away before decaying at a secondary vertex. This secondary point is separated from the primary point by a tiny distance, but the detector can measure it. Tracks that seem to begin away from the main collision suggest that an unstable particle lived briefly before transforming. The distance, direction, and momentum help reconstruct the hidden parent. The particle is gone, yet its path is marked by where its decay begins. Momentum conservation guides, reconstruction. Momentum is the quantity that describes motion and direction. In a decay, the total momentum of the products must match the momentum of the parent, apart from particles that escape detection. If the detector measures all important products, their momenta can be combined. Their combined energy and momentum give an invariant mass, a value that can reveal the mass of the original particle. Invariant mass is called invariant because it does not depend on the observer's motion, in the same way ordinary energy or momentum can. A repeated peak at one value signals a common parent particle. Charge conservation also matters. Electric charge must balance before and after the decay. If a parent particle has a positive charge, the sum of the charges of its decay products must be positive by the same amount. Other quantities, such as baryon number and lepton number, also guide allowed patterns. These rules help scientists reject combinations that cannot represent a given decay. They also help identify possible backgrounds, where unrelated particles accidentally form a pattern that resembles the signal. The decay signature is therefore both a measured shape and a set of consistency checks. Many decay products are common particles such as pions, kaons, protons, electrons, or muons. A pion is a light meson. A kaon is a meson containing a strange quark or strange antiquark. These particles may appear in large numbers in proton collisions. So identification is essential. The detector must decide which track is most likely a pion, which is most likely a kaon, and which may be a proton or muon. A wrong assignment can move an event into the wrong reconstructed mass region. Precision in particle identification is part of the evidence. Background is always present. In a busy collision, many particles are produced. Some unrelated tracks may seem to come from a possible decay when they're only an accidental combination. Some known decays may imitate the signal being studied. Some detector effects may blur the picture. Scientists model these backgrounds using data, simulation, and control samples. A signal is meaningful only after the expected background is described. In the calm language of analysis, discovery means that the signal remains strong and consistent after these ordinary explanations are accounted for. The shape of a signal is often seen in a mass distribution. Researchers combine selected tracks according to a proposed decay pattern and calculate the invariant mass. If the combinations mostly come from random background, the distribution is smooth or shaped by known processes. If a real particle contributes, events gather near its mass, forming a peak. The peak's position gives the mass. Its width can reflect detector resolution and, for some particles, the natural lifetime. The number of events under the peak helps estimate how often the decay occurs. This is how an invisible, short-lived particle becomes a measured object. For rare decays, the challenge becomes greater. A rare decay may occur only a small number of times among many collisions. The selection must keep the signal while rejecting background. It must avoid biasing the measurement. It must account for detector efficiency, meaning the chance that a real event is actually recorded and selected. Efficiency can depend on particle type, direction, momentum, and detector conditions. A measured number of events is not enough by itself. It must be corrected and compared with expectations before it becomes a physical result. Decay signatures also test symmetries. If a particle and its antiparticle decay in slightly different ways, that difference may show CP violation. CP violation is a difference between matter and antimatter behavior under a combined change of charge and spatial orientation. These effects are usually small and require large data samples. LHCb measures decay rates, timing, and angular distributions to search for such differences. The evidence must be handled with caution because small effects can be mimicked by detector asymmetries or production differences. Careful calibration turns a delicate comparison into a reliable measurement. Some decays include neutrinos, which usually escape without direct detection. In those cases, the full reconstruction is harder. Missing energy and momentum become part of the signature. The analysis must infer what is not seen from what is seen. This adds uncertainty and requires more constraints. Even so, such decays are important because they can test the structure of the weak interaction and possible differences between types of leptons. Leptons are particles such as electrons, muons, and neutrinos that do not feel the strong interaction. Their patterns in heavy particle decays have become a sensitive field of study. At this layer, the discovery is no longer a particle as a whole, but a trail of transformations. The original object exists briefly, then passes its information into products that the detector can record. The decay signature is the inner handwriting of the event. It shows where the particle was, how long it lived, what it became, and whether its behavior agrees with known law. Nothing is read from a single mark. The meaning comes from many events, aligned under the same rules. In the quiet work of CERN, decay is not an ending without order. It is the way hidden particles speak through the shapes they leave behind. Within the patterns of decay, a deeper layer appears in the comparison between matter and antimatter. Every known particle has a corresponding antiparticle. The antiparticle has the same mass but opposite electric charge and opposite values for certain other properties. When matter and antimatter meet, they can transform into other particles, often releasing energy in the process. This symmetry between matter and antimatter is a central feature of modern physics. Yet the observable universe contains far more matter than antimatter. The reason for this imbalance remains one of the open questions in science. The standard model includes a mechanism that allows a small difference between the behavior of matter and antimatter. This effect is called CP violation. The term combines two transformations. The first is charge conjugation, which replaces particles with their antiparticles. The second is parity, which reverses spatial coordinates, like a mirror reflection. If the laws of physics were perfectly symmetric under these transformations, then processes involving particles and antiparticles would behave identically when viewed under the combined change. Observations show that this symmetry is not exact. Some decays occur at slightly different rates or with slightly different patterns when matter is compared with antimatter. In heavy flavor physics, CP violation becomes measurable in the decays of particles containing charm or beauty quarks. These particles can decay through different paths that interfere with each other. Interference is a concept from wave behavior, where two possibilities combine and affect the final outcome. In quantum physics, decay processes can interfere in a similar way, leading to differences in rates or angular distributions. LHCb is designed to measure these small differences with high precision. The measurements require large data sets and careful control of experimental conditions. One way to study CP violation is to compare the decay rates of a particle and its antiparticle into the same final state. If the rates differ beyond expected uncertainties, this indicates CP violation. Another method involves studying how decay probabilities change over time, especially in systems where particles can transform into their antiparticles and back again. These systems are known as neutral meson systems. In such cases, time-dependent measurements reveal subtle asymmetries. LHCb's ability to measure decay positions and times allows it to explore these effects in detail. The observed CP violation in the Standard Model arises from a mathematical structure in the theory that describes how quarks change type through the weak interaction. This structure includes complex phases that allow differences between matter and antimatter processes. The amount of CP violation predicted and observed so far is small. While it is sufficient to explain certain experimental results, it is not enough to account for the dominance of matter over antimatter in the universe as a whole. This gap suggests that additional sources of CP violation may exist beyond what is currently known, but no confirmed evidence has yet established such new sources. Measurements at CERN do not assume that new physics must appear. Instead, they test the Standard Model with increasing precision. If a result matches prediction, it strengthens confidence in the theory. If a result differs, it must be examined carefully. Statistical fluctuations, detector effects, and background processes can mimic small asymmetries. Only after these possibilities are ruled out can a deviation be considered significant. The language of significance is precise. It refers to the likelihood that an observed effect could arise by chance. High significance requires consistent results across different methods and data sets. LHCb has reported measurements of CP violation in various decay channels. Some of these confirm known effects. Others explore new combinations of particles and decay paths. In charm decays, CP violation is expected to be very small in the Standard Model, making it a sensitive area for potential new effects. In beauty decays, CP violation is larger and has been measured in several processes. Each measurement adds a piece to the overall picture. The results are not isolated claims. They form a network of tests that must agree with each other and with theoretical expectations. The challenge in these studies lies in controlling asymmetries that are not related to fundamental physics. For example, detectors may respond slightly differently to positive and negative particles. Production rates of particles and antiparticles may differ due to initial conditions in the collision. These effects must be measured and corrected. Control samples and calibration techniques are used to ensure that any observed asymmetry is not an artifact of the experiment. Only after such corrections can the remaining difference be attributed to CP violation. The concept of symmetry at this level is not visual. It is mathematical and statistical. It concerns how often certain outcomes occur and how they are distributed. A small difference in a large number of events can carry deep meaning. The absence of a difference can also be meaningful, setting limits on possible new effects. The study of matter and antimatter in particle decays is therefore a quiet comparison, repeated many times, with careful accounting of uncertainties. It does not produce dramatic images. It produces numbers that must be interpreted with caution. The phrase new discovery in this context often refers to the first observation of CP violation in a particular system or decay mode. Such a result confirms that a symmetry exists in that system and matches or challenges theoretical predictions. It does not imply a sudden change in the nature of matter. It refines understanding. It may suggest where to look next. It may place limits on theories that extend beyond the standard model. Each result is a step in narrowing the range of possibilities. At this layer, the inward path reaches one of the most subtle aspects of particle physics. Matter and antimatter are nearly mirror images, but not perfectly. The small difference is measurable in controlled conditions, using heavy particles that decay in complex ways. CERN's detectors do not see the asymmetry directly. They record decay products, and from those products, scientists extract patterns. The asymmetry appears as a slight imbalance in those patterns. It is a quiet signal, requiring patience to detect and discipline to interpret. The question of why the universe contains more matter than antimatter remains open. Observations indicate that the known sources of CP violation are insufficient to explain this imbalance fully. It remains uncertain whether additional sources exist at higher energy scales or in processes not yet observed. The work at CERN contributes by testing known effects and searching for deviations. It does not claim more than the data support. The exploration continues inward. From decay signatures to symmetry, where even a small difference can carry weight in understanding the structure of the universe. Inside the study of matter and antimatter, the inward path reaches the limits of the standard model. The standard model is the current framework that describes known fundamental particles and 3 of the 4 fundamental interactions: electromagnetism, the weak interaction, and the strong interaction. It organizes quarks, leptons, force-carrying particles, and the Higgs boson into a coherent theory. It has survived many precise tests. It predicts a wide range of measurements with remarkable accuracy, yet it is not considered complete, because several known features of nature remain outside its full explanation. The standard model explains the particles that make up ordinary matter and many unstable particles produced in high-energy collisions. Quarks combine into hadrons. Leptons include electrons, muons, taus, and neutrinos. Gauge bosons carry forces. The photon carries electromagnetism. The W and Z bosons carry the weak interaction. Gluons carry the strong interaction. The Higgs boson is connected with the mechanism that gives mass to elementary particles. These parts form a working map of the subatomic world. CERN's measurements test this map by examining where it is strong and where it may be incomplete. One clear limit is gravity. The standard model does not include gravity in the same quantum framework as the other interactions. Gravity is described extremely well on large scales by general relativity, while the standard model describes particles and fields on small scales. Both theories work in their own domains, but they are not united into one tested framework. At CERN energies, gravity is far too weak to influence ordinary particle collision measurements in a detectable way. Its absence from the standard model is therefore not a daily experimental problem for LHCb or related analyses, but it remains a deep theoretical limit. Another limit involves dark matter. Astronomical observations indicate that galaxies, galaxy clusters, and the large-scale structure of the universe are influenced by matter that does not emit, absorb, or reflect light in ordinary ways. This unseen component is called dark matter. The standard model does not provide a confirmed particle that explains it. Neutrinos have mass and are part of the standard model when extended to include that mass. But known neutrinos cannot account for all dark matter. collider experiments can search for signs of new particles that might connect with dark matter, but no confirmed discovery has established such a particle. Neutrino mass is another boundary. In the original form of the Standard Model, neutrinos are massless. Experiments show that neutrinos change from one type to another as they travel, a behavior called neutrino oscillation. This requires neutrinos to have mass. The Standard Model can be extended to include neutrino masses, but the origin of those masses remains uncertain. The LHC is not the main instrument for measuring neutrino oscillations. Yet the fact of neutrino mass shows that the known framework needs addition. It is a quiet reminder that even a highly successful theory can be incomplete. The matter-antimatter imbalance also points toward a limit. The Standard Model includes CP violation, but the amount it provides is not enough to explain why the observable universe is dominated by matter. This does not mean that the Standard Model is wrong in the measurements it already explains. It means that something about the early universe and the sources of asymmetry remains incomplete. CERN's heavy flavor measurements help test CP violation in quark systems. When the results agree with the Standard Model, they narrow the space where unknown effects could hide. When small tensions appear, they become subjects for careful study. The Higgs boson, discovered at CERN, also opens questions rather than closing the theory. Its discovery confirms a central mechanism of the Standard Model, but the measured Higgs mass and behavior raise deeper questions about why its properties take the values they do. The hierarchy problem is one such question. It concerns why the Higgs boson mass remains much smaller than certain very high-energy scales that might be expected to affect it. This is a theoretical issue, not a direct contradiction in the data. Experiments continue to measure the Higgs boson's properties to see whether it behaves exactly as the Standard Model predicts. The Standard Model is also limited by the number of parameters it contains. These include particle masses, mixing angles, and interaction strengths that must be measured rather than derived from a deeper principle within the theory. The theory describes how particles behave once these values are known, but it does not explain why the values are what they are. The pattern of quark masses, lepton masses, and mixing between particle types remains unexplained. Heavy flavor physics is one way to study this pattern, because quark mixing governs many decay processes. At CERN, possible limits of the Standard Model are approached through precision. If new particles are too heavy to be produced directly, they may still influence measurable processes indirectly. A rare decay may occur slightly more or less often than expected. An angular distribution may shift. A symmetry relation may show a small deviation. These effects would be subtle. They require careful comparison between experiment and theory. The absence of a deviation is also useful, because it sets boundaries on possible new theories. Precision is therefore a way of looking inward without needing to see a new particle directly. Theoretical predictions themselves carry uncertainties. For some processes, especially those involving the strong interaction at low energy, calculations are difficult. A difference between data and prediction can arise from incomplete theoretical control rather than unknown physics. This is why results are compared across several channels and methods. A convincing sign of physics beyond the Standard Model should appear in a consistent pattern, not only in one difficult measurement. The limits of theory and the limits of experiment must be separated with care. The phrase "could change everything" belongs here in its most restrained scientific meaning. A confirmed deviation from the Standard Model could change the direction of particle physics by showing where the current framework fails. It would not erase the many places where the Standard Model works. Older successful theories often remain useful within their domain. Newton's laws are still used for many motions even though relativity gives a deeper description. In the same way, the Standard Model would remain a powerful theory even if new physics were found beyond it. A change in understanding would be an expansion, not a collapse. At this 13th layer, the path has moved inward from particles and decays to the boundary of explanation itself. The Standard Model stands as both a triumph and an unfinished structure. It describes known particles with great success, yet leaves gravity, dark matter, neutrino masses, cosmic matter dominance, and deeper parameter patterns unresolved. CERN's discoveries matter because they press gently against these edges. Some results fill predicted gaps, some sharpen measurements, some reduce uncertainty. The inner region of the topic is not a place of fear, but a frontier of precision, where the known theory remains strong and its unanswered questions remain clearly visible. Near the innermost boundary of CERN's measurements, uncertain signals occupy a delicate region between expectation and discovery. They are not empty noise, and they are not proof. They are patterns in data that differ from a prediction, or patterns that seem unusual when compared with known processes. In particle physics, such signals are treated with care because large data sets contain many possible combinations. Some will look interesting by chance, some will come from detector effects, some will reflect imperfect theory. A few may point towards something not yet understood. The task is to tell these cases apart without moving faster than the evidence allows. An anomaly is a measured difference from expectation. The word does not mean error by itself. It means that a result sits away from the predicted value or from a pattern already established. An anomaly may fade when more data arrive. It may become clearer. It may be explained by a better calculation or a better understanding of the instrument. It may remain unresolved for years. CERN's experiments have seen several tensions in different areas, including heavy flavor measurements. Each one is studied through repeated analysis, independent checks, and comparison with related processes. The first caution is statistical fluctuation. A fluctuation is a random variation that occurs because measurements are made from finite samples. If a coin is tossed a small number of times, one side may appear more often, even when the coin is fair. In particle physics, the samples are much larger, and the mathematics is more complex. But the principle remains. Random variation can create a peak, an excess, or a deficit that looks meaningful at first. As more data are collected, a true effect should persist or grow in significance. A fluctuation often weakens and returns toward expectation. Significance is the formal measure used to describe how unlikely a result would be if only known processes were present. It is often expressed in standard deviations, though in the script the number itself is less important than the idea. A higher significance means a lower probability that the result is a chance fluctuation. Particle physics sets a high threshold for discovery because the data are rich and many searches are performed. A result that is interesting is not the same as a discovery. It must pass strong statistical tests and survive detailed scrutiny. The second caution is the look elsewhere effect. This effect appears when many places in the data are searched for unusual patterns. If enough mass ranges, decay channels, angular variables, or event categories are examined, one of them may show a fluctuation simply by chance. The more places one looks, the more likely it becomes that something will appear unusual somewhere. Scientists account for this by adjusting the interpretation of significance. A local excess may look strong in one narrow region, but its global meaning becomes weaker after the wider search is considered. The third caution is background modeling. Background means known processes that can imitate the signal of interest. If the expected background is underestimated, a normal process can appear as an excess. If it is overestimated, a real signal may be hidden. Backgrounds can be smooth, peaked, or shaped by detector selection. They are estimated using simulations, control regions, and data-driven methods. A control region is a part of the data chosen to be rich in background and poor in signal, allowing the background model to be tested. Strong results require background descriptions that remain reliable under many checks. The fourth caution is detector behavior. Detectors are complex instruments, and their response can vary with time, location, particle type, temperature, radiation exposure, and operating conditions. A small misalignment can affect track reconstruction. A calibration shift can move an energy scale. A trigger requirement can select one class of events more efficiently than another. These effects are not failures when they are understood and corrected. They are part of precision measurement. An uncertain signal must be tested against the possibility that the instrument has shaped the pattern. The fifth caution is theory uncertainty. Some predictions are extremely clean, while others depend on difficult calculations involving the strong interaction. In heavy flavor physics, hadronic effect can complicate the interpretation of certain decays. Hadronic effects are influences from quarks and gluons bound inside particles. If these effects are not calculated with enough accuracy, a difference between theory and data may not mean new physics. It may mean the known physics needs a better calculation. This is why researchers prefer patterns across many related measurements. A single difficult channel is less persuasive than a consistent set of deviations that point in the same direction. Uncertain signals often develop in stages. First, an analysis finds a tension with prediction. Then other teams examine the method. More data are added. Related decay modes are checked. Independent experiments compare their results. Theory groups refine calculations. Sometimes the tension decreases. Sometimes it shifts. Sometimes it remains but loses clarity because new uncertainties are recognized. This process can feel slow from outside the field, but it is the way reliability is built. CERN does not treat uncertainty as weakness. It treats uncertainty as a measured part of knowledge. The public language around these results can become distorted. A small tension may be described as a sign that physics is broken or that new force has been found. Scientific papers usually use more careful wording. They report compatibility, deviation, uncertainty, and significance. They state whether the result agrees with the standard model within errors. They avoid claiming discovery until the threshold is met. The difference between public drama and scientific caution is especially important for titles that suggest fear. The data themselves are not frightening. They are incomplete until tested. An uncertain signal also carries value even when it fades. If an anomaly disappears with more data, it still helps improve methods. It may reveal a detector effect, a background issue, a statistical lesson, or a weakness in an analysis. If a result agrees more closely with the standard model after refinement, the theory becomes more constrained. New physics has less room to appear in that channel. A null result, meaning no observed deviation, is still a result. It narrows the map. It tells researchers where not to look in the same way again. When an uncertain signal persists, it becomes more interesting, but still not final. Persistence across larger data sets suggests that random fluctuation is less likely. Agreement across independent measurements suggests that detector-specific effects are less likely. A coherent pattern across several processes suggests that theory uncertainty alone may be insufficient. Even then, the interpretation must remain cautious. Several possible explanations may fit the same data. Some may involve known physics, some may involve extensions of the standard model. The evidence must choose between them slowly. At this 14th layer, the inward path reaches the zone where knowledge is most easily overstated. The machine has produced collisions, the detector has recorded traces, the analysis has reconstructed particles, and the theory has given predictions. Now the remaining difference must be judged. This is the quiet interior of discovery, where excitement is held inside restraint. An uncertain signal is a doorway only if it stays open under pressure. Until then, it is a measured question. CERN's work in this region is not to turn every anomaly into a claim, but to let data, repetition, calibration, and theory decide what remains. At the innermost point of the story, the question is not whether CERN has found something terrifying. The question is how far measured evidence can carry understanding beyond the surface of what is already known. The phrase new discovery can point toward many different kinds of results. It can mean a newly observed particle, a more precise measurement, a rare decay, a confirmed asymmetry, or a deviation that remains under study. Each kind has its own weight. None becomes meaningful because it sounds dramatic. It becomes meaningful because it survives contact with data, uncertainty, and the wider structure of known physics. The inner question begins with scale. The ordinary world appears continuous and solid. A table, a stone, a hand, a glass of water, and the air above a road all seem to belong to one stable realm. Particle physics shows that this stability is built from hidden structures. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks and gluons. Other particles appear only briefly in high-energy collisions or in natural processes. The familiar world is not false, but it is incomplete when seen only from the outside. CERN's work moves inward through that incompleteness. The inner question also begins with time. Many particles studied at CERN live for extremely short intervals. They appear and decay before ordinary senses could register their presence. Their reality is not measured by duration, it is measured by consistency. If the same pattern appears in many events, with the same mass, charge, decay products, and statistical behavior, then the particle is part of nature's record. A particle that lives briefly can still teach lasting lessons. Its short lifetime becomes a feature to measure, not a reason to dismiss it. The discoveries connected with heavy quarks often refine the strong and weak interactions. A new baryon with two charm quarks shows how quarks can bind in a rare arrangement. A rare decay tests whether the weak interaction follows expected patterns. A matter-antimatter asymmetry shows how symmetry is slightly broken. An anomaly asks whether prediction and observation are fully aligned. These results do not all carry the same meaning, but they share the same method. They emerge from collisions, pass through detectors, become data, and then face analysis. The inner question is always what the pattern truly says. The standard model remains central at this depth. It is not a fragile theory waiting to be destroyed by one result. It is a powerful framework that has absorbed decades of testing. Its limits are real, but its successes are also real. It explains much of the behavior seen at CERN, from particle production to decay structures. When a new hadron is observed, it often fits within the standard model. When a measurement agrees with prediction, it strengthens the map. When a tension appears, it marks a possible edge, but not yet a new territory. The theory is both guide and boundary. The unknown lies beyond that boundary. Dark matter, neutrino mass, the matter-antimatter imbalance of the universe, and the absence of gravity from the standard model all show that the current picture is not complete. CERN does not solve these problems by force. It approaches them by measuring the places where known physics might leave a small opening. A decay rate may shift. A symmetry may break in a new way. A particle family may reveal an unexpected member. A distribution may refuse to match prediction. The unknown, if it appears, may first arrive as a small difference. This is why precision matters more than spectacle. A large machine is built not only to create high energies, but to make clean comparisons possible. The beams must be stable, the detectors must be calibrated, the simulations must be tested, the background must be understood, the statistics must be strong, the theory must be stated with its uncertainty. Every step reduces the chance that a false pattern is mistaken for a real one. The inner question is protected by this discipline. Without it, the unknown would be confused with error. The language of fear often grows around what cannot be pictured. Quarks, gluons, antimatter, quantum fields, and hidden particles do not fit easily into ordinary imagination. They seem strange because they are far from direct experience. Yet the science itself is not built from fear. It is built from limits. A detector has limits. A theory has limits. A measurement has limits. A claim has limits. CERN's strongest discoveries respect these limits. They do not make the universe less stable. They make human description more accurate. The idea that a discovery could change everything needs a calm meaning. In science, changing everything rarely means erasing all that came before. It means changing the frame in which old facts are understood. A new particle can complete a family. A new asymmetry can alter the search for cosmic origins. A confirmed deviation can guide theories beyond the standard model. A precise agreement can close a path and redirect attention elsewhere. Each change is measured by how it improves the connection between evidence and explanation. At the deepest level, CERN's work is a conversation between what nature allows and what human instruments can detect. Nature does not present its smallest structures in direct view. It leaves traces, a curved track, a displaced vertex, an energy deposit, a missing balance, a mass peak, a decay rate, and a small asymmetry all become part of the language. Scientists learn to read that language slowly. They do not read every mark as revelation. They ask whether the mark repeats, whether it fits known rules, and whether it remains after doubt has done its work. The inner question remains open because science remains active. Observations indicate that the standard model describes a large part of particle behavior with great success. Observations also indicate that it does not explain every feature of the universe. It remains uncertain where the next confirmed step beyond it will appear. It may come from a collider measurement, a neutrino experiment, an astronomical observation, or a form of evidence not yet available. CERN contributes by making some of the smallest tests as precise as possible. The path inward ends not with alarm but with attention. Above ground, the laboratory stands among roads and fields. Beneath the region, the ring guides beams. At the collision points, particles appear and vanish. In detectors, traces become data. In analysis, data become measurements. In theory, measurements become pressure on the known framework. The innermost region is the quiet place where a question remains after all exaggeration is removed. What is matter? And how complete is the present map of its rules? CERN's discoveries matter because they keep that question alive under the discipline of evidence. The laboratory grows quiet again in thought. The roads above it remain ordinary, and the fields hold their stillness under changing light. Beneath them, the great ring becomes only an idea of motion, a circle shaped by cold magnets, empty pipes, and careful timing. The beams, the collisions, the traces, and the measurements settle into one slow image of patient inquiry. CERN does not turn the unknown into fear, it turns the unknown into work. A particle appears for a fraction of time and is gone. A detector records the signs left behind. A computer gathers the patterns. A researcher compares them with what is already known. Some results confirm the map. Some add a missing detail. Some remain uncertain and wait for more evidence. In this way, discovery becomes steady rather than sudden. The deepest lesson is not that matter is fragile, but that matter is layered. The visible world rests on atoms, nuclei, quarks, fields, forces, and probabilities. Much is understood, and much remains unfinished. The Standard Model stands as a strong structure, while unanswered questions remain beyond its walls. Dark matter, neutrino mass, cosmic imbalance, and gravity still wait in the distance. The story ends at the quiet edge of knowledge. The machines do not roar in the imagination now. The detectors do not flash. The particles do not need drama to be real. They leave their signs, and the signs are read slowly. What remains is a calm inward view of nature, precise, unfinished, and open.